Well, let's try a few of the problems from the practice final here. The actual final will be much shorter. But suppose I want to find partial derivatives, right? I can start at W, and if W is a function of x, y, and z, it's 4x squared plus 4y squared plus z squared. I draw these branches down. And then x, y, and z are the spherical coordinates, say. X is rho sine phi cosine theta is a function of rho phi and theta. Y is a function of rho phi and theta. And z technically is only a function of rho and phi, so you can put just down those two down if you want. And now if I want to take, let's say, the partial of W with respect to phi, this one, dW d phi. You just chain along going down the tree, you take all paths from W down to phi. So there's this one, and here's this one, and here's this one. So we got to remember there's partial derivatives that go along these branches here, dw dx here, dx d phi here. So it's dw dx, dx d phi, plus along this branch dw dy dy d phi, plus along this branch dw dz, dz d phi, well dw dx is apparently 8x. That multiplies dx d phi is rho cosine phi cosine theta, treating rho and theta as constants. So you're taking partial derivative, treating the other two variables that go with it, rho and theta as constants. And now dw dy similarly is 8y. That multiplies dy d phi. Well, y is this function, partial with respect to phi, treating rho and theta as constants, is rho cosine phi sine theta. And then should have said dw dz, is 2z, multiplies dz d phi, which is minus rho sine phi. And you're not done until you put it all back in terms of rho, theta, and phi, so I'll call this 8 times rho cosine theta sine phi times all this stuff, rho cosine phi cosine theta, plus 8y is 8 rho sine phi sine theta. That multiplies rho cosine phi sine theta. And then I've got to add to that 2z, which is 2 times rho cosine phi, multiplying minus rho sine phi. Add all those together, and you got the partial derivative. Let's try doing directional derivatives. If I want the directional derivative of a function 4x cubed times y squared at the point 2, 1, this would be the slope of the tangent line. At this point on the surface z equals 4x cubed y squared. In the direction moving 4I minus 3j, what is it? Well, remember to evaluate the directional derivative, duf, you take gradient of f dot u, where u has to be a unit vector in the direction you're moving. So first thing I'll do is I'll take the direction I want to move, 4 minus 3, divide it by its length, and get 4/5 minus 3/5, right? This length is the root sum squared. Squared is 4 squared plus 3 squared is 5. So this is the unit vector in the direction I want to move. Then I need the gradient. The gradient is a vector of partial derivatives. I take partial with respect to x and get 12x squared y squared. Partial with respect to y, I get 8x cubed y. And I take that vector and plug in the point 2, 1, and I wind up with 48i plus 64j. So the gradient at that point is 4864. The direction I want to move at that point is 4/5 minus 3/5, and I take their dot product to get the directional derivative. It comes out to be 0. We just happen to move or directly orthogonal to the direction of steepest descent. What is the direction of steepest descent? Right, the idea is you've got a tangent plane of the surface. If you move in the direction of steepest descent, you've got one slope. You move perpendicular to that, you get 0 slope. All right, so suppose I want direction of steepest descent. Recall that's the direction of the gradient. So the gradient was 4864. If I divide that by its length to get a unit vector, I get the vector 3/5, 4/5. That's the direction of steepest descent, is the gradient divided by its length. And if I take the gradient of f dot u, a vector of the same direction, then I take 4864 dot 3/5, 4/5 gives me 80 for the slope of the direction of steepest descent. All right, let's try this. Suppose I want to find the minimum and maximum values of 4x cubed plus y squared, subject to a constraint that 2x squared plus y squared equals 1. Remember, optimization subject to a constraint. Find the highest point on this mountain subject to the constraint that you walk along this trail in the xy plane. It can be done by the Lagrange multiplier method. It says that for these problems, gradient of f is lambda gradient g, where g can be gotten by writing this equals 0. Rewrite it as 2x squared plus y squared minus 1 equals 0. The problem counts as g of xy equals 0. Maximize or minimize f of xy has this requirement. Gradient of f is lambda gradient g. Well, here's the gradient of f, the vector of partial derivatives. 12x squared is partial with respect to x. 2y is partial with respect to y. We get this vector. Partial of g with respect to x is 4x. Partial of g with respect to y is 2y. So we get 4xi plus 2yj. Setting these two equal means their components have to be equal, right? So 2x squared has to be lambda 4x. 2y has to be 2y lambda. So it's easy now to divide through by x and y and think that solves everything. If you divide this one through by y, you find out that 2 equals 2 lambda, so lambda has to be 1. Once you know lambda is 1, then you can put it into here and find out that x has to be a third. And once you know x is a third, you can put it into the constraint. Keep the Lagrange, keep the gradient of f equals lambda gradient g, 2 equations. Also, you need the constraint. These has 2 equations with 3 unknowns. The third equation makes it 3 equations with 3 unknowns, gives you the solutions. So I'll put x equals a third down into here, assuming lambda equals 1, and get y equals plus or minus square root 7 over 3. These are 2 points that satisfy the Lagrange multiplier equations and the constraint. But wait, we're not done. Be careful when you divide through by x here, you assumed x wasn't 0. When you divide it through by y here, you assumed y wasn't 0. What are some solutions, maybe where if y equals 0 satisfies the equation instead of lambda equals 1? Well, if y equals 0 to satisfy this equation, then I plug that in here, and from the constraint I find x equals plus or minus 1 over square root 2. And then I can fit lambda to make the last equation work. Or if I put x equals 0 in this one, then if assuming lambda is in 0, well, let's see, if x equals 0 in this equation, then I get lambda isn't restricted here. This one then says I can't have y equals 0 or I can't satisfy the constraint. This one now says lambda equals, let's see, lambda equals 1 to make this one work since 2y isn't 0. And then if x is 0, y has to be plus or minus 1 to make this one work. And so you get this set of 6 points, and you plug all those into the original function, the largest is going to give you the max, the smallest is going to be the min, because you know a max and min occurs. Be careful that you know a max and min occurs. In this case, we don't. We do, excuse me. Sometimes when the constraint curve goes out to infinity, there is no max or min. But this one is a polynomial function. I don't know what it looks like. This is surely not the graph, but suppose it looks like that. It's a continuous function, and it's subject to this constraint, which actually is an ellipse. So you're constraining yourself to moving on an ellipse in the xy plane, and then there's a path on the surface overhead, which is a continuous surface. This means you have a continuous curve moving up and down in 3 space. It's going to have a min and max, so you just have to plug these in, see which gives you the largest, which gives you the smallest. Find out the largest occurs at 1 over square root 2, 0, gives you f equals square root 2. The smallest one, x equals minus 1 over square root 2, 0, makes f equal minus square root 2. There were 2 types of line integrals. One was the scalar line integral, where you integrated a function ds, and the other was the vector line integral f dot dr, which is defined in terms of the scalar line integral. Suppose we do a scalar line integral, just an integral of a function ds. Here's one integral 1 over 1 plus x along this curve with components t, 2/3 t to the 3/2, t running from 0 to 1. Take the line integral of this function. We have a theorem that says you can evaluate it by integral of f of x and y replaced by their functions of t, length of dr dt dt. You can think of this as being the little infinitesimal arc length ds. And so x is equal to t from the parametric curve. This is 1 over 1 plus t. Length of r prime of t is the root sum square of the derivatives of these. Derivative of t is 1, derivative of 2/3 t to the 3/2 is t to the 1/2. So that we get square root of 1 plus t here, times 1 over 1 plus t gives us integral of 1 over square root 1 plus t. Now you can evaluate this integral by substituting u equals 1 plus t to make this 1 over square root u. When you do, du is derivative, dt is just dt. But now t went from 0 to 1, u is 1 more, it goes from 1 to 2. So when I integrate u to the minus 1/2, you can write this as is u to the 1/2 over 1/2, or 2u to the 1/2. Plug in the endpoints and take the difference. You get 2 square root 2 minus 2. Alright, here's a vector line integral. Line integral along the curve f dot dr. Suppose that path I want to evaluate it along as a conservative vector field. In that special case, I can use the fundamental theorem of line integrals. I can just evaluate the potential for that function at the final point minus the potential at the beginning point. It doesn't even matter what path got there. Right? So here's a vector field. Let's check first that it's conservative. You can check by making sure that the g dx equals df dy. Or you can just try and compute the potential, and if you can find one, then it is actually conservative. So I'll just try and compute it thinking it is conservative. Here's, if it's really a potential, then it's the gradient of some function phi. This must be d phi dx, and this must be d phi dy for it to be a gradient. So if this is d phi dx, I can integrate that with respect to x and get phi, and I get this. Just integrating, this is a partial integral, so I treat y as a constant. I get x cosine y plus y cosine x, plus an arbitrary function of y as a constant in a partial integration. Then this must be the partial with respect to y if f is the gradient of phi. So phi must be the partial integral of this with respect to y. And when I integrate this treating x as a constant, I get y sine x minus x sine y plus x cosine y, plus an arbitrary function of x as a constant in partial integration. So now, if it's really a conservative vector field, then phi has to match on these two. Can I match these? In order to match these, well, these are equal and these are equal. These can only be constants because this is a function of y alone, this is a function of x alone. They must be, in fact, just a constant. So here's the most general potential. I have found one that is both the partial integral of this with respect to x and partial integral of this with respect to y. Given that this is the potential of the line integral, this is the potential of the final point minus the potential of the end point, we which is pi over 2 sine pi over 4, just plugging it into the potential, plus pi over 4 cosine pi over 2, minus the potential at the other endpoint is 0, and we wind up with pi over 2 square root 2. Alright, here's number 10, Green's theorem. Suppose I want to evaluate a line integral. This is also vector line integral, the other notation. F of xy dx plus g of xy dy is just another notation for f dot dr with f having this component and this component. So suppose I evaluate this one by Green's theorem, where you can only apply Green's theorem to a closed path, and it applies for counterclockwise paths. If it's clockwise, you just get minus this result, but for a counterclockwise path, say it's this one around the rectangle, the 1 by 2 rectangle, what is the line integral of f dot dr in this case? Well, you call this little f of xy, and this little g of xy, and Green's theorem says you can double integrate it over the region it bounds, dg dx minus df dy. So dg dx, so I wrote that wrong, is 2y, and df dy is then 3x, and you try and evaluate this over the rectangle. Well, it's just a double integral. This one a partial integral, and then this outside one, you wind up with 3 halves.